Hi everyone, my name's Orta therox, and we're going to go through how the compiler compiles. So a deep dive into TypeScript's sort of architecture as a code base, with a sort of focus on this sort of pipeline where TypeScript reads a file off the disk, sort of turns that into something in memory that it can then use to type check, and then eventually sort of emitting some JavaScript or source map files and things like that. To get an understanding, I'm assuming you know what TypeScript is, but we're going to sort of ground this first in understanding what the repo looks like and what the code base is. TypeScript's been around for quite a while, and you might not be surprised to know that TypeScript is built in TypeScript. It's a self-hosted language. It's about 250,000 lines of code at this point, at least specifically in the code that gets shipped to the NPM module. Test sets and other files sort of really make that much bigger, but this is like the useful code. There's about 80,000 separate test files. The way in which TypeScript's testing systems work are generally that you have a sort of before and after integration style testing system. There's about 5,000 files that make up TypeScript's main export, but for us, there's realistically somewhere around 8 sort of mega files that contain most of the work. If you follow the repo, you get quite a lot of notifications. That's like 70 a day roughly. And TypeScript's actually 11 years old at this point and has been through 2.5 rewrites. It was first created in F# at the same time as the C++ version were being built. And then it was sort of released as a self-hosted version of TypeScript, so it was built in TypeScript, and then it was rewritten then at version 1.1 to go from this kind of classes style to a very functional style. For this talk, the target audience is basically someone that's interested in kind of understanding how the TypeScript compiler works. Like, you may not actually be interested in contributing to the code base, but if you are interested in contributing to the code base, this is a really great sort of primer over all the different components inside TypeScript. This talk is built to sort of work with this other talk that Anders gave back about 5 years ago now on the modern compiler construction. So the different mindset he had when he was helping to architect what TypeScript would look like over time. It's a really great talk. I recommend it. It's not quite like this in that it will help you necessarily understand the TypeScript compiler, but it will give you a very high level understanding of why some of the things are the way they are. So to get started, we need to sort of first go in and look at the sort of main way in which you would interact with the TypeScript compiler if you were using it from the compiler API, and that is via an object called the program. And I like to think of it as sort of a project coordinator. And it's 4,000 lines of code, which in the scale of things to come isn't that much, and it has this sort of responsibility of handling the entire pipeline. In fact, when you do TSC on the command line, it is mostly the program setting up a bunch of work and letting it do it, and these are the sort of the main pieces of that work that happens. So for example, your code would generally look like this. You would first create a program, giving it a set of files. Then you would say, tell the type checker to, run the type checker over those files. You might not actually be interested in type checking. You might just want to use TypeScript to transform a TypeScript file to a JavaScript file. So this is optional. And finally, then there is the emit phase, which is sort of taking the in-memory representations and turning those back into files. And so these sort of 3 major sort of steps are how we're going to go through the TypeScript code base. To get further docs on the sort of program and more of the internals, how you can use it as an external user, you can go and read up on how the compiler API works on the TypeScript wiki. So I talked about these 3 separate areas, and these are sort of the framing of this talk. We're going to go through source code to data, which sort of represents the tokenizing and parsing section of this diagram. We're then going to talk about type checking, which sort of talks about the binding and the type checking phases. And then we're going to talk about creating files, which is sort of, getting things out onto the disk and having something that actually has emitted some files. So thinking about it from source code to data, we're going to work with this bit of sample code. It is, it is effectively free statements. Statements are a JavaScript way of describing code that's sort of evaluated as a single chunk. Traditionally, you would see a semicolon at the end of every single statement, and that's like a good rubric to understand where a statement ends. In this case, this code has 3 separate statements. That's the first statement that generates this variable called MSG. The next statement will then call a function called welcome with the MSG, and then the third one will set up a function called welcome. If you think about this as being, something that lives inside a TypeScript file, then you can start to get this sort of tree shape in your head where there's a TypeScript file, and inside that are a bunch of statements. This works, and then, to fully represent the source file, we have to go a bit deeper, and we have to start sort of chunking out through each statement what part of, what sort of bits of code exist inside each statement. And in this case, we are effectively seeing, chunks of words separated at this point by spaces, turning into something that lives inside a statement. And this is effectively what we call the syntax tree. It is just nested sort of nodes inside nodes inside nodes that each represent a little bit of sort of JavaScript or TypeScript code. Now, you'll probably have also heard abstract syntax tree. You may have never heard concrete syntax tree, but both of those are effectively in modern compilers very much the same. So if I accidentally say abstract syntax tree, it's the same thing as me just saying syntax tree. We don't have too strong opinions in the team about it. The way that we create a syntax tree is via a scanner and a parser. These are the sort of 2 main objects that have different types of responsibilities that come together to generate the syntax tree. So for the first one, that's the scanner. The scanner is 2.6 thousand lines of code, which is tiny, and because of that, it's actually quite a simple concept. So the scanner's job is to sort of take some text and go from left to right, and whenever it sort of sees a space or something that it knows is a change of context, it will sort of emit a syntax token. So it will effectively say, hey, const, okay, yeah, and there's this white space. Okay, so if there's a white space and the text inside it is const, then that's probably the keyword const. And you can't have a const in the as a name, as an identifier in JavaScript. So the scanner just throws up the word const keyword. Then it sees a space. So it says, hey, I've seen some white space, and then I've hit a new thing after, which is an identifier, and so on and so on and so on. It's very sort of linear. And in the process of doing so, you can start to get a sense of, trying to understand a little bit about what the code is in terms of how we perceive it as people using the language. To get a better sense of what the scanner does on any code, there's a Playground plugin called TS Scanner. You can find it in the plugins tab, and you can pass any code, the JavaScript or TypeScript, and it will tell you what the results of running the scanner is over it. And the scanner will sort of give you these error messages that really talk about how there is no legitimate JavaScript where this could happen. So, if there's no ending quote in a JavaScript file, then JavaScript engine doesn't know when to finish evaluating, so it will just halt. And the same as you'll get a runtime error instantly if you do 2 underscores in a numeric literal. And so the scanner sort of sees these things and is like, okay, we're just going to raise an error straight away. The scanner is then sort of manipulated by a parser, and the parser is starting to hit some pretty solid lines of code at 9,000, and its job is effectively to bring context to the scanner. So the scanner passes the parser a bunch of syntax tokens, and it's really on the parser to say, hey, okay, so you've passed us in a const keyword. That means we're probably at the start of a variable declaration. And a variable declaration always lives inside a variable statement. And so I, as the scanner, as the parser, will set up this tree in such a way that the next thing that comes in is going to be, you know, the next thing that comes in, which would be the identifier. That's going to be used as the name of the variable that we have just started declaring, and the scanner effectively adds understanding about where the parser adds understanding to the scanner in order to give a correct syntax tree. So these two sort of work in tandem. You know, the scanner will sometimes get rewound because, you know, the parser has decided that we're in a new context now, and it is really the job of the parser to create a correct syntax tree, but it asks the scanner to do a lot of the sort of left to right reading, and it thinks at a higher level of abstraction. So the syntax tree is something you get quite familiar with when you start working with tools in JavaScript and other languages, because you don't necessarily want to always be working on text. There's 3 great ones for working with TypeScript and JavaScript, and that's AST Explorer, which is a pretty general AST Explorer. It works across many different tools and languages. There's the TypeScript Playground, which has an AST viewer inside it too, which is pretty good. It's not the best, but and I made it, so I can say that. And there's the TypeScript AST viewer, which is generally very, very good if you're doing compiler work, and sort of the thing that I need to make as good of for the website. All of these are strongly recommended and really provide different interesting lenses on what the syntax tree is. For the parser, a lot of the diagnostics that it throws are all related to you know, the right JavaScript in the wrong place, right? So, you know, this hash myvar in the first case, that's a private class variable, and realistically they can only live inside a class. So if you use it outside of that, then it will know that that is incorrect, whereas a scanner, on the other hand, would not know that it's incorrect, because its job is just trying to figure out what the things are and then just sending them up. So with the 2 of those down, we would now have a series of sort of TypeScript syntax trees. And syntax trees are what all of the type checking works on. So the next step now is to start thinking, hey, what are these objects and how do they relate to each other? And so there are 2 sort of systems in play when you want to do type checking. There is the binder and the type checker. So the binder is one of these concepts that when you first sort of see it, you're not quite sure how to fit it in your head. And after playing around with a lot of different explanations, the one that fits most for me is the idea that to run through an entire source file object, to run through an entire syntax tree, and to pick out bits of data that we will need for type checking is quite expensive. And what TypeScript tries to do is to try and only have one sort of tree run that will do as much sort of metadata grabbing and manipulation and setting up separate similar hierarchies and do all those sort of things at once. And we call that entire system the binder. But realistically, it's actually a series of different responsibilities, but done in a single pass. So to give you a sense of what this sort of looks like I just picked a single web page from the TypeScript website and sort of tried to get a sense of how many nodes there are for every single file. This is about 250 lines of code, and it makes quite a lot of nodes. If you do that for every single JavaScript or TypeScript file in your entire code base, you can get a sense that there's an awful lot of trees that would need reading. And so the binder really just sort of jams all that into a single place. The 4 main responsibilities that it does are creating these symbol tables, which we'll go into quite depth next, setting up the parent on syntax tree nodes. So think about it as like at any point you'll be able to go all the way up to sort of investigate when you're type checking what the parent is and what the parent's parent is, stuff like that. Making flow nodes. So when you're thinking about control flow analysis, that is set up at this point. And then sort of validating script versus module conformance, which we'll also get into. So what the binder does for setting up the symbols. Symbols are something that like you think about in your head, but you don't necessarily have a word for it. One way to think about it is that the way that you process code is that you think of different scopes. Here we have a global scope which represents all of the code that lives inside this sample, and inside here we also have a second scope for inside the function. On the global scope there's a set of variables that are available to it, so there is MSG and welcome, but inside welcome, the scope for that function, there is also str, which is a parameter that's come in from the creation of the function. So you can get the sense of like, different places in the code base or different parts of identifiers that are available to it. And what the binder does is effectively sets that up. So we start going from left to right via this sort of tree traversal system, and start picking out when we have seen identifiers and where they were declared and what sort of flags can be applied to them. So in this first case, we've found MSG and we've sort of declared that it exists on line 0 at certain indexes and said, hey, this is a variable and it was block scoped when it was found. Next, we see the welcome, but the symbol type doesn't do much with it at this point because it hasn't been defined yet. It's there, but it's not actually useful for us to know that it is there. And just like we've just seen with welcome, this second MSG is also then not actually used per se because the definition has already been defined for earlier. We then see that the definition of welcome has been found, and now anytime the welcome, the symbol has been found, it knows how to get to the original definition of it, which also then helps to provide where the type could be defined from. And then, because we have nested scopes inside this code, then we create a new symbol table with a reference to the parent. So in the case of the function scope of welcome, if you looked for MSG, it would know to go, well, it would not find it in the function scope. It would go to its parent, which would be the global scope, and then it would find MSG inside that table. And because it's a new scope that's a function, it adds the parameters into the new scope inside. And so that's sort of like the symbol table. So symbols are effectively a way of keeping track of identifiers across files, and they're done on a very, very global scope, and then sort of narrowed down further. If you want to get a sense of what the symbols look like, I made a TypeScript playground plugin that allows you to sort of define what a bunch of additional symbols on the top level of your playground, and then you can just run this, press this button, and it will list out all the different flags and declarations of each symbol that it's found. This is really interesting if you're sort of doing compile dev. I find it fascinating. One of the next responsibilities of the binder is to think about the flow nodes. And in this case, we can't really talk about the code flow analysis because there's not actually any code flow analysis that needs to be done with this source code. So we're going to switch it out and have a new code sample. And again, if you think about this, how you think about it as a programmer, as a user, you would sort of make this mental jump in your head, right? You know that X at the start of this function represents something that's either a string or a number. Then further down, it's used again in the type of, and it's still one of those two things. When you get inside that if branch, then it is either a string or a number, depending on the if or the else. And then once you back outside, then you are back to a string or number. And this system basically needs to be set up in a way where TypeScript can keep track of sort of what contains these variables, a lot like the scopes that we saw earlier, as well as keeping track of where a mutation for these identifiers could occur. So the first thing it does is it sets up these flow containers. there's a flow container at the global scope, and then it moves further and further down, very similar to the symbol tables. And what happens there is that there's also sort of flow conditionals created. And these are sort of, this is a very high level representation of it, but these are effectively mapped to the actual nodes in the syntax tree that sort of show you where the flow conditionals and where the containers live. And this sort of creates a new visual, a new graph basically of how code flows inside your actual code. And so the way that we try and think about it in TypeScript is that we create this flow graph that that always travels upwards. So in this case, right, we have the function container of the entire function, and inside that function we have an if condition for true and an if condition for false. And in all of these cases, whenever whenever we need a type checking the type of X, then TypeScript will sort of use this flow graph and go upwards to keep asking, hey, how could the type of this type be affected by code flow analysis? So to give you a sense, we'll sort of dig what it looks like to go through it. So if we started with this first X, it would be at the top of the function container. And so at that point, it would go up into the next sort of scope and look through its flow nodes. But it's defined there, so it doesn't matter in this case. The next one, it's still going to go to the closest function flow container, which is still the function container, because at this point, we haven't actually hit the conditionals because we're inside that conditional at this point. Now, when we hit this X inside, then we will first hit the closest conditional. The closest flow conditional, which will then be seeing that it's on the side of true. And then TypeScript will do the work to decide, hey, what is the bit that has been constrained, and that's all handled in the type checker. But at this point, the binder is just saying, hey, these nodes exist in the flow graph. These are the things that you'll have to respect when the type checker actually does the type checking. And then the same for the else, where it's on the opposite side of that conditional. And then for this side, this X actually has to check all of the flow nodes. It checks every single possible route on its way upwards, because at this point it's still possible that the X has been changed by different conditionals inside your code. For example, you may have a return statement inside one of these if statements. So if you had if type of X equals string return X, then X at the end can only ever be a number, which means we need to take that into account when you're doing the sort of code flow narrowing. Whew. So that's the flow nodes, and the binder then, to think about it from what sort of error messages the binder gives, the binder gives messages that sort of, they understand a lot about the context. They have already seen that the entire, the binder has already seen a full syntax tree, whereas prior to this, everyone has been building a tree bit by bit by bit. And so it can create sort of diagnostics that understand the entire context of the source code file that you have there, with the biggest one being strict versus module. Being script versus module, which has implications around strict mode. And that's not strict mode in TypeScript, that's JavaScript strict mode, which is a sort of parsing mode that says, identifiers can only be put in certain areas and you can't delete a thing in certain contexts. And so the binder then raises a few diagnostics that would be a little bit surprising to you if you didn't realize that the binder was this sort of single pass tree parser. As well as the binder, it sets up those symbol tables, which means that it can also then set up the duplicate type checks. So, in this case, that's a class and a type. They're two very different, well, they're not entirely different types of things inside the system, but they are both considered different if they are primitives with the same name in the case of TypeScript. So next up is the type checker. It's a very big file. It's 42,000 lines of code right now, and it does what it says in the tin. It checks your code. It's very big. It's really interesting to sort of dig into. For this talk, we're still talking at quite a high level. There's space for a really in-depth type checker talk, probably about the same kind of length. But to really, to narrow down why I don't have to dig in too deep to the type checker, almost every talk about TypeScript and about, how TypeScript's, structural typing system works and why unknown is better than any, all of these concepts are like, they are valid explanations of how the type checker works. And that is effectively how this 42,000 lines of code file works. And so I will cover it at a different sort of level that they will, but I don't need to cover all of it in an extremely extensive way in order to give you an understanding of the high-level architecture of TypeScript. So the TypeScript type checker does actually give most of the diagnostics, which makes a lot of sense considering it is the thing doing the checking. It has sort of three main systems that we'll try and talk about here, like how it checks structurally, so like how as a code pattern it thinks about checking, how it compares types, and what sort of inference systems are inside the checker. So to think about how the type checker checks, it is it's a file where for almost every syntax tree node, there is a corresponding check function. So in this case, if we were checking the code, does this string match this other string, TypeScript will be iterating through the syntax tree, checking each individual part of it. So it first checks the variable statements, and then the variable declarations, and then it checks whether one part of the variable declaration is assignable to another part. So in this case, we'll use it as an example. We're checking is every possible string assignable to a specific instance of a string, an exact literal, if you will. And in this case, actually, TypeScript doesn't necessarily do a full structural type analysis, in part because these are two primitives. And what happens is the type checking parts of the system, the bits that most people describe a lot of the time, it's short-circuited here. And we use the first check is simple type related to. It's this really useful sort of quick bit that just checks a few flags to say, hey, if this is a string-like thing and this is a string-like thing, they're pretty much the same thing. We can just move on now. We don't need to do a much deeper analysis. And so in this case, actually, this check is actually, it does hit this flag. One of them is string-like and the other is a string. And that returns true. And so these two are considered the same in the TypeScript structural analysis. So for something a little bit more complicated, example, these two objects, we start at the outside and then sort of work our way in. So there's a structural analysis on the outer parts of the object. So in this case, it's an object to another object, and that would actually hit the is simple type related to also because they're both objecty. And that would sort of move on into, hey, what fields are available inside this object? And it would start at the first one, in this case, hello, and then it would check, hey, do you have a return type? Okay, if you do, then are these two assignable? And it's at this point that the checker would fail on these two objects, as you would have probably imagined in your head. The same analysis is mostly the same for like type generics. It can get a little complicated with like covariantness and contravariantness, but I'm not going to get into that too much. Or at all, but in this case, you get the sense that like a promise is checked to a promise. These would be the same symbols that would just keep moving on, and then it would check the inside, so it would check the type arguments inside that promise, and it would say, okay, so the first type argument is a string assignable to an object, that would fail, and that would say no. And so that is done using the sort of is type related to code. One of the systems for inference that comes up very common is initializer inference. So like the process of taking code like this and actually instead writing code like this, where you don't write what the type is ahead of time. You just say, well, I just wrote what the end result of this expression is, and so that same type is going to be available inside my type. And so how that works is reasonably simple. We looked earlier at the syntax tree for this const message equals hello world, and there was a bit where we said what the type was, and now that it's been taken away, and all that is left is effectively in the tree name and initializer. And what TypeScript does is the type checker just does a type check on what the result of the initializer is and just move that into the type. So it's quite simple. It's usually like the first sort of thing you build when you're doing type inference. Something that's a little bit more nuanced here is type parameter inference. So think about this as we don't know what this t is in this type. Because it needs to be defined further down. So in order to understand what t is by inference, you need to define an object with a function that has a return type, and that return type is what we're going to say is going to be t in this case. So to understand that, you need to first think, okay, so there's a generic argument called t, it has a return value that is also t, and then the param of that is the object. So to give an example, we're going to say const abc equals setup my object, and that object is just going to return a string. So this is the usage of which TypeScript is now going to have to try and figure out what the type for the function setup actually is when it's starting to do type checking. And how that works is, again, like a lot of these things sound very simple, in part because a good idea is it starts to dig down until it finds a match for the missing t. So in this case, it looks and sees that there's it has a parameter, and that parameter is an object. So it looks inside the object, sees it's an object that matches in the usage. Okay, then it checks to see if there's an initial. If there is an initial, then it checks to see the return type. It now has then understood that the t in this case represents the return type of initial, which is a string. And so this work is actually sort of done ahead of time in the checker when it's starting to compare a lot of the different types. And what the type checker does, it sort of creates a new instance of this setup function in its head, where string has been set for all of the t values. And so this is now done as though you had hand coded it like this, and passed that now into the type checker. And so when TypeScript is now type checking the actual usage of setup, what it's actually doing is comparing with the new version in memory that has strings set in all of the right places. And so you can think of it as like going quite deep down into the usage to sort of extract out some useful type information, and then bring that all the way back up and sort of restating what the original function looks like in the type system. Whew. There we go. That's me re-explaining that, but in text. The next one is quite a similar concept, actually. It is contextual typing. And this is one of those sort of tools that people use to really give a great editor experience with very little syntax added. We're going to look at a definition of an object that has a function called inc that has a number parameter and returns a number. So we can see it's an object, it has a function, and this is the usage of it. So we're going to have the declaration of adder, and then we're going to add this this bit of type that says, hey, this entire thing, this thing is an adder. I know it. Now the question is then, how can TypeScript go and add information about what n is behind the scenes for you? So we see that there is an adder and it has this function already, and it starts to become TypeScript's responsibility when it sees this n. Until this point, it hasn't needed to sort of figure out what the details are in this, because the comparison has been pretty safe. But at n, we need to start applying some type knowledge to try and understand what it is. And the steps to do that are quite similar to what we just talked about. It is to sort of first go back up through the tree. So think about it, a syntax tree goes down, so you're going back up the tree to sort of through its parents to understand what's going on. So it looks to the n and it says, hey, what is the definition of n? Actually, we don't know this. So TypeScript goes, hey, we're going to look at the function. Hey, does this function have any sort of type analysis applied to it? And strictly speaking, it doesn't. Only like contextual typing isn't applied at this point. Then we have the object, and is there any type information here that could give you information about n? Not enough yet. It's only when you start to look at the full object that TypeScript has gone back far enough to see that there is a thing called adder applied to this entire object. And then it's sort of TypeScript's responsibility now to take this adder and go back down. So we know that adders are an object, so that the objects match in this case, so we can keep going further and further down. Then we can see that adder contains a function called increment in its type, and so does my runtime version of it, which must mean that the corresponding n has a corresponding type because they're in the same position inside that function. And so you can think about it as going back down through this, going back up the syntax tree to find that type that corresponds after going back down again. And it kind of works in an interesting way. And that's why you can sort of write a single type at the top of a long expression and just allow the types to flow through it naturally, because every time TypeScript hits a type that it doesn't understand what the type is, because it's not enough information, then it will scroll, it'll go all the way back up through the tree, try and find the closest type that could correspond to that entire object in this case, and then try and figure out what the types could be corresponding to that. So TypeScript has to do a bit more work in these cases, and that's kind of the price you pay for less syntax, but it's very elegant and it's a very clever system. And so that's generally the type checker. The type checker is big concept, lots of ideas, lots of things going on, and to really sort of get an understanding of it, like my best recommendation is to actually get the TypeScript compiler cloned locally, make a test file that has some code that you think is interesting, and then just put a debugger in some of the sort of check XYZ functions inside the checker, and just follow it around. See how things work. That's how anytime I have to sort of fix a type checker bug, that's how I try and figure it out. And you get really good at using the debugger when you're working in the TypeScript code base, because there's just lots of functions everywhere, and the debugger really is useful in our stack trace, and I'm a big fan. So we talked about sort of type checking, binding, and now it's time to sort of look at, okay, so we've got some files and some syntax trees. How do we actually emit something useful? How do we say what the JavaScript version of a TypeScript file is? So the responsibility for this is the emitter. It's sort of this one file that handles taking source syntax trees and turns them into files. It has sort of four major responsibilities. It knows what sort of files need to be emitted and kind of how. So, there is a sort of bundle all JavaScript into a single file mode. There's knowing whether to output map files and some of the other files. Then there's keeping track of the variables inside a single file so that you don't have clashes with identifiers, as well as then sort of printing, which is kind of one of the big responsibilities of the emitter, as well as applying transformations to whatever your syntax trees look like. So to get a sense of transformers, we're gonna give you an exact example, actually. This is what happens when the TypeScript transformer is applied to this part of the syntax tree. So the TypeScript transformer wants to get rid of any TypeScript specific syntax. And so in this case, what it does is it goes through the tree, sees that there is a type definition in this variable declaration, and just drops it from the tree. There we go. Now suddenly we have legitimate JavaScript code because the type parts of that part of the tree is just not there at all. And so TypeScript has quite a few transformers, and all of these transformers work on a syntax tree. So, you know, there's remove TS syntax, class fields, and then it goes through all of the different ECMAScript versions, and then a sort of module transformer that handles whether you're doing requires, UMD, AMD, things like that. And finally, there's an ES5 transformer. And this is the longest it could possibly be. It's as if you had never set up your TS config. A more realistic one might be something like this, where you have, you know, you're going all the way back to target ES 2017, and after that, then it doesn't do any more transformations because TypeScript doesn't need to go any further down in your syntax. And you can visualize all of these if you're interested in the TypeScript playground. There's a plugin called Transformer Timeline that shows you each step. As you can see in this example, there's not actually that many steps that run on this specific source code that I have, so it's usually a bit better when you've got more complicated TypeScript, or JavaScript, I guess. One interesting part of all this is that, like, I spent so much time describing in the binder just how much we don't want to be doing syntax tree walking. And yet I've just shown you this graph that has tons and tons of syntax tree walking, and you know the emitting of JavaScript is an integral part of TypeScript, and don't we want to keep that fast? Well, there is this interesting set of rules during the creation of the syntax tree that keeps track of what sort of transforms are going to be needed later on down the line. So we have these three statements, and it sort of corresponds almost exactly to this syntax tree shape. And what happens is that when they are being created, each part of this tree knows which parts will need changing later down the line. So, you know, by including the type parts of the first statement, the colon string, the creation of that syntax tree will add this fact that's called assert TypeScript, which means that the TypeScript transformer will need to do some work on this one. The next line, the welcome MSG, needs no transformation, even if it goes all the way down to ES3, which I believe is the default is in TypeScript. And then the next one will also need some TypeScript work, but only to get rid of the colon string again in the third statement. And these tree facts are then used to sort of reduce the amount of possible work necessary for individual transformers to do. So it's very rare that they actually do a full syntax tree dive. They just know which parts of the tree will actually need to be run. It's interesting that the DTS transformations are also a syntax tree transformation. You know, in this case, we're actually, for a DTS emit, we want to get rid of the runtimey aspects of it. And so in this case, we take away the initializer aspect of the declaration, and that just leaves us with MSG colon string. Which is basically what the DTS version looks like. And then we add an export in this case. Sometimes that's a bit more complicated, right? So that example I gave, the previous one had colon string, but in this first example, we don't actually have a type, right? Like you can't just remove the initializer, because if you do that, then you just end up with nowhere. And so what happens is the emitter asks the type checker, hey, what is the type of the initial expression that used to be here? So what is the initializer's expression? What is that type? In this case, we get the hello world, and that is then put in its place. So it's just, you know, syntax-aware transformer that can rely on the type checker when it needs to do some sort of gap filling. This entire system is roughly how a JavaScript DTS emit is done. Think about it as like, ahead of time, TypeScript looks at a JavaScript file, says, "Oof, there are no type initializations anywhere," and just asks it at every single point, "What is your type?" And then those are then filled in generating the TypeScript DTS emission. So kind of interesting. It's just a sort of pre-bit of work that only exists when it's JavaScript to a DTS file. And so that was the entire summary of all of the different pieces that sort of come together to create the full TypeScript pipeline. There's quite a lot going on there, as you can imagine. And most of the names correspond to the things that we said there, so you can just search for emitter and that'll give you whatever you want in the TypeScript codebase. And I hope this gave you a good sort of overview of how TypeScript's codebase is architectured, as well as trying to inspire you to understand some of the sort of more nuanced aspects of how the sort of the air quotes magic works behind the scenes. There's lots of really interesting ideas and abstractions inside the TypeScript compiler, and if you play around with it from the inside, I think you sort of get an appreciation for just how complex but understandable a lot of these ideas are. So thanks for watching. Hope to see your contributions to the compiler. Bye.